Hi everyone, my name is Andrew Toffik. Today my colleagues and I will be talking to you about quantum Jacobi forms and sums of tails identities. This is joint work with Professor Amanda Folsom over at Amherst College. So I will be mostly discussing the preliminaries in order to get the groundwork out the way, in order for my colleagues to then come in and further discuss our results. So my plan is to guide you through to quantum Jacobi forms, but we found that the best path to them is through first introducing the one variable case, modular forms, and showing how things were built on top of each other in this case, then mirrored into the Jacobi world. So instead, we'll be first talking about what a modular form is. So a modular form is a type of symmetric function that takes values in C, the complex numbers, and is defined on H, the upper half plane. This has a weight attached to it, which is typically an integer and sometimes a half integer. This function is holomorphic on the entire domain and at infinity. And now there's quite a bit of symbols here, but it more or less says that this function is symmetric under the group action of 2 by 2 matrices of determinant 1. You can just think of that as saying that modular forms are a type of infinitely symmetric complex function. So as for some examples of modular forms, here is one that stems from geometry. In particular, this is what's called the J function, which is intimately connected with the theory of elliptic curves. Here's another example, this time from combinatorics, and this is the partition generating functions, whose coefficients keep track of different ways to sum up to an integer. And lastly, here's an important example from the theory of q-hypergeometric series, which is where my colleagues will be greatly focusing on. This here is called the q-Poch hammer, and this is how the q-Poch hammer is defined, and there are both finite and infinite variations, where this is just chosen to be infinity instead, and we'll see this more and more as time goes on. So you might notice up here in the G function, for instance, it's taking input of tau, yet there's no tau that seems to be showing up in the actual definition of the function. Well, that's because in the theory of modular forms, a common substitution that is made is sending tau from the upper half plane to Q, a point inside the unit disk. Here's that being visualized. And notice that all the points in the upper half plane necessarily get mapped into the interior of the unit disk. So this is worth keeping in mind because this will implicitly come up over and over again over the duration of the talk. So now that we've talked about modular forms, let's talk about what happens when we introduce some sense of error to it as well as change the domain. That is to say, here again is the definition of modular forms. And now let's just change this modular transformation definition a bit. Well, not actually change it, but just move all the terms to one side as well as divide. And we get this. Again, same exact information as in the definition of modular forms. But now let's talk about what happens if this upper half plane domain is now changed to be the boundary of the upper half plane, which is Q. So what the question then becomes, if we introduce this sense of error or change our domain, what can we say we want this modular transformation to be equal to? We can't let this error term be 0, because if we let it be 0, we end up getting a trivial definition for this variant of modular forms. So what we can do is we let this be defined to be a function h, and we ask this error to extend to a suitably continuous or analytic function on the real numbers. Now the reason this is left purposely vague is in order to encompass as many possible examples of modular forms as we can. Now notice as well, this is actually a very recent definition put out by Zagier in 2010, so quantum modular forms are still being actively searched for today. Now that we've talked about modular forms and introducing some sense of error to them, it's safe to move to the world of Jacobi forms, where we're introducing a second variable. Notice how the input has changed as well as some of the properties. So let's now go into this in a bit more detail. A holomorphic Jacobi form has now a weight and an index, and it is a holomorphic function on C cross H. And in the variable that's on H, there's a modular transformation. Now notice how much this resembles the definition of modular form we saw earlier. And this is primarily acting on the second variable. So as a result, the second variable is often called the modular variable. And on the first variable, it has this elliptic transformation property. So again, as a result, this is usually called the elliptic variable. This is somewhat old, as you can see, so Jacobi forms have been around for quite a while, of course not as long as modular forms. And again, we can proceed how we had before with going to quantum modular forms, where we introduce some sense of error. We can do the exact same thing here in the Jacobi case. So here's the definition of a quantum Jacobi form, where now we're on Q cross Q, and we have this error, which corresponds to the modular error, And we have this error which corresponds to the elliptic error. And now, again, this is left somewhat vague in order to encompass as many different examples as we can. Quantum Jacobi forms, as you can see, are very, very new. And we don't actually know that many families of quantum Jacobi forms. So one big thing we were trying to do in this research is try to find more quantum Jacobi forms. Excuse me. So again, here is everything we've so far discussed. We will be focusing primarily on quantum Jacobi forms and how we can get more of them. And now, with that being said, I will hand this talk off to Noah.
Thanks, Andrew. My name is Noah Solomon. I'm going to be talking through some of the details going on in the subject and our work in particular. We've now seen definitions for quantum modular forms and quantum Jacobi forms, so a natural question to ask is, what do they actually look like? When Zagier first gave the definition of a quantum modular form in 2010, one of his first examples was the Kontsevich phi function. As you can see, this is a function from the rationals to the complex plane, and we were again using the same change of variables from x to q that Andrew mentioned, although in this case the inputs are in the rationals rather than in the upper half plane. Again, we have the same q-pockhammer symbol that Andrew defined, and as you can see, it is a product of binomial terms where the subscription notes the number of terms in the product. Zagier showed that this Kontsevich function is a quantum modular form with weight 3/2. How then did Zagier prove that this unusual function was in fact a quantum modular form? Well, a key ingredient in his proof was the use of this identity, which we will call a sum of tails identity. We are using the q-pockhammer symbol again here, and chi of n is -1, 0, 1. There's a lot going on here, so let's break this down. On the left-hand side, we have what we will call a sum of tails. There are two important things to note here. First, we can see there is a striking resemblance between this expression and the Kontsevich phi function. The two key differences are that the expression above includes an infinite q-pockhammer, whereas the phi function involves only a finite q-pockhammer. Secondly, the Kontsevich function converges only on the rationals, while Zagier's identity is defined only in the upper half plane. The second thing to note is that the sum is a difference between an infinite product, highlighted in red, and a finite product, highlighted in blue. This is precisely what we mean when we say that this is a sum of tails. We can think of this definition more generally as an expression summing over an infinite product minus a finite product. As we saw in Zagier's identity, we also want the limit of the finite product to be the infinite product. So the expression on the left-hand side is connected closely to the Kontsevich function and is a sum over tails of an infinite product. So what about the right-hand side? As you'll recall, this somewhat involved expression is what appears on the other side of Zagier's identity. There are a lot of symbols here, but if we focus just on the first term, what Zagier was able to show is that the term highlighted in orange was in fact a quantum modular form, when considered as a function defined on the rationals. So what we have on the right-hand side then is a quantum modular form when considered on the rationals, but is currently being defined on the upper half plane. We also have the infinite product term, so there are two things we need to deal with. Recall that our quantum modular forms are defined on the rationals. In addition, our Kontsevich function is defined on the rationals and indeed only converges there. However, the identity that Zagier wrote down is true for tau in the upper half plane, so we need to shift our input. As you recall from Andrew's discussions, the change of variables from tau to q maps the upper half of the complex plane to the open unit disk. Additionally, as you can see here, the boundary of the upper half plane, the rationals, gets mapped to the boundary of the open unit disk, roots of unity. What Zagier did was to consider the identity as tau approaches rational numbers, or equivalently, as q approaches roots of unity. Starting with the left-hand side, we can see that as tau approaches rationals, the infinite q-pockhammer symbol vanishes, and we're left with a sum over finite products. In a similar fashion on the right-hand side, as we let tau get close to rationals, the term involving the infinite product vanishes, and we get just the first sum. Considered together, we can see that the terms involving infinite q-pockhammers vanish towards rationals. Putting the sides back together, we can see that the terms highlighted in teal, those involving these infinite products, vanish towards rationals. So we have this kind of asymptotic almost equality. So from Zagier's original identity involving a sum of tails, he was able to get this asymptotic statement, which is a lot simpler. But what exactly does this get us? Well, first of all, the left-hand side is exactly the Kontsevich phi function. We don't need to worry about the domain here because we are considering this statement as tau approaches a rational number, which is precisely where phi is defined. On the right-hand side, we have exactly the expression that Zagier showed was quantum modular. So through this asymptotic equality, the Kontsevich phi function inherits the quantum modular properties and is therefore a quantum modular form. Now we understand what Zagier did to prove that this one function, phi, was a quantum modular form. So we ask, how can we emulate this strategy to find others? Like Zagier, we want to start with an identity which holds for tau in the upper half plane, and we want to require a few key components. First, we want to have some kind of sum over tails on one side, in just the way that I outlined before. Second, we need a quantum modular form on the right-hand side. Lastly, we need these annoying extra terms to vanish as we let tau tend towards a rational number. That is to say, to use Zagier's methods, we need a sum of tails identity that satisfies the two other key properties we used in order to show that the Kontsevich function was quantum modular. As you'll recall, we were actually interested not in quantum modular forms, but quantum Jacobi forms, so we also need to add a second variable. A natural question to ask is if we can use the same general kind of strategy to find a quantum Jacobi form. The idea then is to get a two-variable sum of tails identity like this. Again, not just any sum of tails will do. We need the expression on the right-hand side to contain a quantum Jacobi form when considered on pairs of rationals. And of course, we want to be able to do the same kind of asymptotics as before, except now we let W and Q approach pairs of rationals. This is our key strategy and question this summer. Can we use special two-variable sum of tails identities to find new quantum Jacobi forms? Remember as well that while modular forms have a long and storied history, quantum modular forms have only existed since 2010, and these quantum Jacobi forms were only defined in the last 5 years. All sources of them come from only a small handful of papers, so it's an exciting time to be looking for new examples. From there, I'll hand it off to Lizzie, who will tell you a little bit about what we found.
Thank you, Noah. My name is Lizzie Pratt, and I'm going to discuss our results. So first of all, we have these 4 new two-variable sums of tails identities that we found this summer. Now for the first 3, it's fairly clear to see that we're summing over the difference between a finite product and its infinite counterpart. So they're indeed sums of tails. And then for the 4th one, it involves this Pn of WQ, which is a certain combinatorial generating function that we're not really going to get into for the sake of brevity, but it does have W squared QQ infinity as its infinite counterpart. So great. Now we have these new sums of tails, and our next question is, can we use them to find quantum Jacobi forms? So we know that, as in the one variable case, when we approach the rationals, the infinite products will disappear, except for this time we're approaching Q cross Q from C cross H. And this gives rise to our next theorem, that the following q-hypergeometric series are actually quantum Jacobi forms. And the proof of this has 2 parts. One of them is using this sums of tails to show that asymptotically as we go towards pairs of rationals, we will get a q-hypergeometric series on the left and these thetas on the right. And the next part of the proof is to actually show that the thetas are quantum Jacobi forms. And we do that by relating them to known families of quantum Jacobi forms. And this exactly mirrors what we did for the one variable case, where we had a q-hypergeometric series, the Kontsevich function on the left, and a known quantum modular form on the right. And so you might ask, well, if we already know that these thetas are quantum Jacobi forms, what do we really get from the sums of tails? And the answer is that this hypergeometric series way of writing the functions is actually really useful in a way that we'll see in the next few slides. So why do we like q-hypergeometric series? One reason is that they make evaluating quantum Jacobi forms much easier. So the function theta 3, for instance, can be evaluated in 2 ways. One is to use the asymptotic expansion that sort of comes from this family of known quantum Jacobi forms, and that is related to the first way of writing the function, where this character is actually the same character that appears in the Kontsevich function. The second way is to use the q-hypergeometric series to evaluate it. And you might think, well, this seems kind of hard, don't we have this infinite sum? But it turns out that when you plug in pairs of rationals, the infinite sum will actually truncate. For example, if we plug in 1/2, 1/4, and look at this q-Pochhammer expression, it contains the term 1 minus WQ squared. And when we plug in, we can see that that's 0. And in fact, all of the q-poc hammers with n greater than or equal to 2 will contain this 1 minus wq squared term. So all of them will disappear, leaving us with a sum that actually truncates at 1. And as you can see, that makes the evaluation at 1/2, 1/4 relatively easy. Now, the final interesting property of these sums of tails that I'm going to talk about is a relationship between the two variable sums of tails that we found and certain one variable sums of tails. In particular, if we look at our example again, we can see it kind of looks very similar to the one variable sums of tails we found that was related to the Kontsevich function. And it turns out that if we differentiate the two variable sums of tails in W and plug in W equals 1, we will get exactly the one variable sum of tails that we had multiplied by a factor of q to the negative 1/24. But it's essentially the same, and that's really interesting by itself. And the other interesting thing you might note that as a result of this is that we took a q-hypergeometric series in two variables that we know is a quantum Jacobi form. We applied this differential operator, and then we got back essentially like a slight normalization of a quantum modular form. And that's something that was very interesting to us. So we tried doing the same thing to our other identities, that is differentiating in W and plugging in W equals 1. And we got the following one variable sums of tails as corollaries. And it turns out that in all of these cases, these sums of tails are actually already known. And what's more, they give rise to quantum modular forms, theta 1, theta 2, and theta 3. So this gives us a very interesting relationship between our quantum Jacobi forms and known quantum modular forms, namely that you can differentiate the quantum Jacobi forms in W and plug in W equals 1 to get quantum modular forms. And that's a really interesting trend that we'd like to look at more in the future. So just to recap, this summer we found several new two-variable sums of tails identities, some q-hypergeometric series that are quantum Jacobi, and this really interesting derivative-based relationship between our identities and some known quantum modular identities. Here are some more resources that you can look at if you want to know more, and please feel free to ask us any questions, and thank you for listening to our talk.